In this section, we're going to take a look at polynomial functions, and the first thing I'd like for you to do is to remember something we saw happen when we talked about quadratic functions. We talked about this word called zeros, and we talked about its relationship to the factors of a polynomial. And what we learned from that section was that if x minus c is a factor of a polynomial, then x equals c is a zero. And it works in both directions. So if x equals c is a zero, then x minus c is a factor. And this fact extends to larger polynomials as well. So when we're asked on number 1 to find the zeros of this function, we're asked to set each of the factors equal to 0 and then solve. So technically we could say 4 equals 0. We could say x squared plus 36 equals 0. We could say x minus 4 equals 0. And we could say x plus 6. You can put the squared on it if you want. It's going to eliminate in a minute as well, but equals 0. Now on the first one, clearly we know that 4 does not equal 0, so this doesn't give us any solutions. And if we were to take a look at solving this, this would say x squared equals negative 36. And we remember from what we've been working on that squares, if we take a square root, that is to say, of a negative number, we get imaginary values, and we're only working in the real number system, so this doesn't give me any solutions. The next one, when I solve it, sure enough does, so I get x equal to 4. And on the last one, I can take a square root of 0, which is not super exciting, but I end up getting either way that x plus 6 equals 0. So x is equal to negative 6. So I have two solutions, negative 6 and positive 4. Now let's think along those same lines again and do another very similar question. Again, asks us to find the real zeros. Now I'm not going to write down 2 does not equal 0 again. I think probably one time of writing that was enough. I really just need the variable terms, right? I need to know that I have that x minus 3 is equal to 0, and that I have x squared minus 25 equals 0, and that I have x plus 3 squared equals 0. Although I will say, we talked about that just a moment ago, that squaring doesn't affect anything, so we could just write x plus 3 equals 0 from the beginning. So the first one is x equal 3. The second one says x equal 25, and then of course when I take the square root I get a plus or minus. So x is actually equal to plus or minus 5 from that middle one. And then if I subtract 3, right, I have x is equal to negative 3, the rightmost one. So I actually have the 4 zeros, 1, 2, and this one that says plus or minus is worth 2. There's 4 that are there. Okay, so you might notice though that it seems like, the squaring of it, like at the end x plus 3 squared equals 0, doesn't affect the zeros. And in reality it does. It does affect them, but it affects them in sort of a non-direct way. So we're going to talk about what's called multiplicity, and multiplicity is simply how many times each zero or factor occurs. And if that number happens to be an even number, like it was over here where I had the squared at the end, right here, right? Then it actually just comes down and it just touches the x-axis. So it looks, something like this, and it bounces back off. Hang on, I'm going to try that again. Yeah, so that's pretty close, right? It just touches, barely touches the graph, it bounces back off. And then the other option is that if it's an odd number for the highest power, right, on that value, the power on that value, then it actually would cross the graph at that value. Right, so it actually cuts through the graph, say right here, when we were getting something that's an odd exponent power. So we're going to go back and take a look at the values that we got in the first two examples, and we're trying to state the multiplicity of each one and what it means. Does it tell you if it crosses it or that it cuts through, or that it bounces off of it? So on the first one, x equals 4, this would have a multiplicity of 1 because it only shows up one time. And because it's odd, it means it crosses the graph. On the second one, this one actually has a multiplicity of 2, which means it simply touches. I shouldn't have said crosses the graph, I should have said crosses the x-axis. Let me go back and fix that. That's better. It touches the x-axis on the other case. All right, thinking more with that, along with multiplicity, we can actually go the other direction as well. So we can actually take values that are zeros and we can create the polynomial that goes with them. So let's give it a name. And then I've got the 1 over here, right? So the fact is that since it's a 1, I would have x minus 1. And because this is a multiplicity of 2, I need a power of 2. The next one is 0, so I have x minus 0. And then minus 7 will be x minus the negative 7, or x plus 7. And then negative 9 is minus a negative 9, or positive 9. And for the purposes of what we're doing, we can actually leave that one. I'm not asking you to multiply it out or anything like that. All right, we've done x and y intercepts before. Y-intercepts, of course, are usually the value at the end that's a coefficient. And we can find them usually pretty directly. So let's do the y-intercept actually first. Y-intercept is when x is equal to 0. Usually easier to find because it's often solved for y. So here y equals the same as f of x equals. And it's 3 times 0 cubed plus 3 times 0 squared, and then plus 18 times 0. So lots of zeros, of course. Here you get a 0, so my y-intercept is 0, 0. But you might notice that not only is that a y-intercept, but that's actually also an x-intercept, right? So let's find the x-intercepts, and we'll actually see that one occur again. X-intercept is when y equals 0. Of course, y is another name for f of x. So the function itself equals 0. So I've got 0 equals 3x cubed plus 3x squared plus 18x. Sorry, minus 18x, my bad. All right, so for starters, you'll notice there's a 3 common to all the terms, so we'll factor a 3 out. Oh, I'm sorry, and an x common to all the terms as well. Okay, going a little too fast, 3 and x. And then I've got an x squared plus x minus 6. And if I keep going one more step, it'll be in factored form. It'll be plus x plus 3, x minus 2. All right, and then on each of these, we're going to set them equal to 0. Like so. So in the first one, x is equal to 0. On the second one, x is equal to negative 3. And the last one, x is equal to positive 2. So all of these ordered pairs are paired up with y equals 0. So 0, 0, that's my very first one, right? Negative 3, 0. And 2, 0. Okay, a couple of vocab things going on in the next 2 slides. Degree. Degree is the largest exponent in a polynomial, and the leading coefficient is the coefficient of that polynomial. So the coefficient of largest exponent term. End behavior is the tendency of the y values on the far right or the far left sides of the graph. So what is going on the far right? What is going on the far left? That is what it's called end behavior. All right, so looking at end behavior, we have a couple of possibilities. One possibility is that we have an odd degree, right? So the highest exponent is something that is odd. And it has a positive leading term. So leading coefficient is positive. When that happens, on the right-hand side of the graph, we're going to have a part of our graph going up to infinity, eventually. There may be something else in the middle, but eventually. On the left-hand side, if you go far to the left, you will have values that are below the x-axis, right? So the idea, though, about this is that it rises to the right and it falls to the left. Now, thinking about that, we can actually do the same thing with an odd degree. So an odd degree means that we are going to have the same thing as before, but now it says a negative leading term. So it's going to flip. I'm going to end up having a increasing to the left motion and a decreasing to the right motion. Okay. There's 2 more options, of course. I could have even degree terms. If have even degree terms and it's positive, the graph would look like the ends of a parabola. I would actually have parts of my graph going up on the right and on the left. And if it's negative, it just flips this upside down. So instead of having it right and left being up, you'd have it being down if you were working with the leading, or finding the end degree, and you have finding the end behavior for an even degree if you have negative leading terms. All right, so we've just a few here left. We're going to find or describe the end behavior. So it's all about the highest degree term, which is x to the fifth in this one, and it's odd. It's odd and it's positive. And because of these features, we know that it rises to the right and it falls or decreases to the left. Okay, so on part B, technically you could multiply this out to answer the question. It's a bit of overkill, not really necessary. What you want to recognize is that if you did multiply this out, you'd have a term that says x squared and some other stuff, right? And over here you'd have a term also that says x squared and some other stuff. And these are being multiplied by the negative 3x at the beginning. So when I multiply these out, eventually I will end up with a negative 3x to the fourth plus or minus a bunch of stuff. The issue is that it is even and negative. And even and negative actually looks like this one on the there we go, on the right hand side, right? Even and negative, they both point downwards. So as we're describing this, we can actually talk about the fact that this has that it falls to the right and it falls to the left. All right, last example is a graphing calculator example. If you were to put this into your calculator and you were to look for where the minimum occurs, we talked through how to do that in the last lesson. So you graph it, you put this in Y1, and then you hit second, trace, and there will be an option there, I think it's option number 3, that says minimum. You left bound it, right bound it, and guess, and then you're good to go. So on this one, I would like to note with you what we have in terms of the degrees. This has a odd degree, but it has a negative coefficient. If we actually had a different function, it would change some of those things potentially. So since it's odd degree and it's a negative coefficient, and we're looking for the place where the graph comes down, it looks something like this, and we are looking for that point. And you can use the lower and the upper limits to find that particular point. And if you do, what you'll find is that, again, we're approximating to 2 decimal places, negative 1.72. Sorry, I said 72 in a row, 75. It's supposed to say 72. And negative 1.27. Sorry, I lost my place there for a moment. So again, the calculator actually is the one finding those values for us. And if you have any questions about how to find those, or it's not quite pulling up on your calculator, please come and see me.